procedure is alkaline is being used in cleaning the reactor at first, and then using clean water to rinse it, and followed by acid cleaning, then followed by clean water rinsing again. Then after that, sterilization is performed, and neutralization is followed, and finally to sterile rinsing. So this is the CIP system, and then the next one will be hazard analysis. So the hazard analysis is being done to analyze the type of hazard which can happen during process. So the first parameter is temperature, which is if the temperature is higher than 80, then this may cause enzyme to denature and reaction rate will reduce. And then this may be caused by the failure of So the action required is to ensure maintenance, checking frequently, and then provide additional backup, calibration on temperature indicator. So same goes to lower than 80 degrees C. It's due to failure of control valve or of cooling medium maybe, and then consequence may cause enzyme activation reduce, reaction rate reduce, and the action required is the same. So it's to ensure maintenance and provide additional backup. And then the next one, this is for the lower part, lower of 80 degrees C, which is same as previous one. And then the next parameter will be flow rate. When at a high flow rate, it may cause by failure of control valve, and then this will cause overflow and reactor may explode due to over amount of the mixture in the tank. And action can be done by ensuring maintenance and operating be caused by failure of pump, and it can reduce production rate. So action will be provide additional backup and ensure maintenance. So if there are no flow rate, may be due to pipe leakage, and this can delay production. So action also will be ensure maintenance and provide alternative pipe to replace the old one. And then the pH, if it is more than pH 7, it can cause enzyme denature, and then reaction rate will decrease. So it may be caused by failure of pH indicator or controller, and it shall be done by ensuring maintenance and provide additional backup. And then the next slide. At lower pH of 7 may due to malfunction of pH indicator and controller, enzyme activity decrease and reaction rate decrease, and ensure maintenance and provide backup. So at a high level of mixture may be due to failure of control valve and indicator and controller. So it can cause overflow and reactor may explode. Same procedures being indicator and controller, or due to pipe leakage, and this can cause underflow and lower production rate. So the procedure is also the same as the previous one. So that's all from me. I will pass to the next person. Thank you.
Okay. The next one is process and mechanical design for my part. It's a bioreactor but with different reaction, which is the saccharification reaction. Okay, firstly for the overview, after the slurry from the previous process is liquefied, the slurry will be entered to the bioreactor to further process, which is the saccharification, by using enzyme alpha glucosidase. So this is where the product from the with previous process will be formed into various oligosaccharide, which is known as isomaltooligosaccharides. And then this alpha glucosidase enzyme can occur two different reactions, which is will occur simultaneously, which make the reaction is complex. Okay. For next one is the equipment consideration for the bioreactor. Okay, firstly is the construction of the bioreactor, which is made of stainless steel that will easy for the cleaning and sterilization. And for next, and second is the reactor will be equipped with the stirrer that to ensure that the mass transfer process can occur efficiently. And then the next one is the tank will be fitted with the baffles to prevent a large central vortex from being formed, and also can improve the mixing behavior in the vessel. And then the vessel will be equipped with the jacket to maintain the temperature for the enzymatic process, which is 65 degrees Celsius. Okay, this one is the summary of the process design. Okay. Firstly is the operating temperature, which is 65 degrees Celsius, and the reaction time for the process is 16 hours. And then the mass flow rate and for the liquefied slurry is 4010 kg per batch. Mass flow rate for the outlet 4012 kg per batch. And the inlet temperature is 65, but there is a decreasing of temperature based on the calculation from SuperPro, which is the outlet temperature will become 64 degrees Celsius. And then the water for maintaining the temperature is assumed to be 35 degrees Celsius and outlet 30 degrees Celsius. Okay, next is the mechanical drawing. Okay, this is drawing that I draw using the SolidWorks software, but because I can open my AutoCAD in my laptop, so I use SolidWorks. Alternative is SolidWorks. Okay, next is the dimension for the bioreactor that I designed, which is the height is about 2.6 meter, with the diameter of the reactor 1.3 meter. The support used is the leg support, which is 0.09 meter. Then and the impeller diameter, which is about 0.43, and then the blade for the impeller, which has length 0.107. And then the height of the impeller above the floor is about 0.43, with the and then finally is the nozzle diameter, which is used for the discharge, and for the inlet and outlet of the feed is about 42 millimeter. Okay, next is the cost analysis. I divided with the major equipment and the minor equipment that used for the bioreactor. Okay, firstly, based on the calculation, the jacketed vessel major equipment, which is about 299,000 ringgit, and then minor equipment that I use is valve, pump, temperature probe, and pH probe. And this temperature probe and pH probe is important to maintain the condition for the reaction to occur. So the total cost for the bioreactor that I designed is 307,000 ringgit. Okay, next one is the PNID for the bioreactor for centrifugation process. Okay, firstly, this bioreactor has feed, so the flow rate of the feed has to be controlled. And then the most important is the temperature in the reactor. So this is important for the reaction to occur. So the temperature transmitter will be equipped, and then the temperature controller will regulate the bath for the hot, water medium. And then the discharge is equipped with the level controller where this is batch process, so the valve will be not open until the reaction is settled. Okay, next is the CIP system for the bioreactor. This is almost same with the previous one, which is firstly is a pre-rinse cycle where the water will be wet the interior surface of the tank to remove the remaining residue, and then there will be a caustic wash that use sodium hydroxide at 75 or until 80 degrees Celsius that will circulate through the equipment to ensure that all product contact. And then there will be an intermediate rinse where the fresh water will flush out the residual traces of detergent from the caustic wash. And then there will be a final rinse with the water to remove all the alkali from the caustic wash and from the system. And then there's an occasional acid wash that will for every 6 months after the alkali enriching step using the nitric acid. Okay, this one is the Hazoop analysis for the my bioreactor. And firstly, the parameter that will be analyzed is the temperature. When the low temperature, that might be because of the leakage of the hot water under hot water pipeline, and also the low water supply. And then when the low temperature, the reaction cannot be occur, so the action required is such as the install the low temperature alarm, and also the daily inspection. And then for the for high temperature, the cause might be from the poor heat transfer or the high water supply. That this one will make the temperature will build up in the reactor, so the reaction cannot be utilized. And then the action is install the high temperature alarm, and then there's also maintenance, periodic maintenance and inspection for the heater. Okay, next one is the parameter is for flow. Okay, when there is no flow, there might be from the leakage and the blockage of the loss of feed supply. When the feed is not coming through the reactor, so there will be no reaction. And then the control action is daily visual inspection and install no flow alarm. And same with the low and high, there will be effect the reaction of the medium in the reactor. Okay, next one is the agitation. When there is no agitation, there is maybe the malfunction from the stirrer motor. There will be no mixing process, and then there will be possible accumulation of unrated materials. So the control action is the motor have to be thoroughly checked, and then the proper lubrication of motor may be applied. And then for the high agitation, this is maybe because of the stirrer motor, and then that will make the impeller will run with high RPM. Then the control action is proper inspection and maintenance. Okay, then that's all from me.
Okay, I will proceed with the process and mechanical design for membrane filter. Next. Okay, so for ultrafiltration, suspended solids and solids of high molecular weight are retained in the so-called retentate, while water and low molecular weight solids pass through the membrane in the filtrate. This separation process is used to industry and research for purifying and concentrating macromolecular solutions, especially protein solutions. In this process, we want to filter protein, alpha amylase, and also alpha glucosidase. Next. There are many modules of membrane. This is my model configuration. There are many modules of membrane that can be chosen from, which is tubular modules, hollow fiber, spiral wound, and plate and frame. But I chose tubular module because tubular system have less falling compared to plate and frame system, and similar amount of falling when compared to spiral and capillary. Tubular system also allow for robust cleaning methods. And then we have two modes of operation for filtration, which is cross-flow and dead-end mode. But I choose cross-flow filtration because it can reduce falling, and also the permeate flux does not drop as fast when compared to dead-end filtration because cross-flow removes build-up from the surface of the membrane. And then the molecular weight cut-off for this design is 3000 daltons, which is lower than the molecular weight cut-off of protein, alpha amylase, and alpha glucosidase. Next. This is the summary of membrane filter design, which is, the parameters is from SuperPro software. The operating pressure is 4 bar, the inlet pressure is 8.3 bar, and the outlet is 0.7 bar. The inlet temperature is 64.3 and the outlet temperature is 66.5 degrees Celsius, which does not change too much. Next. So this is the summary of membrane filter design. The material used for membrane properties is polyether sulfate, which is usually used for ultrafiltration process. And then the length is 0.61 meter, diameter is 0.16. The membrane area is 1.3 meter square. The flux is 16.04. And then the process time hour for our ultrafiltration process is 1 hour. Diameter pore size used is 0.005 micrometer. The membrane thickness is 0.5 micrometer. And the membrane resistance is 9.08 times 10 per PAS per meter. And then the number of tubes of our membrane properties, our membrane is 18 tubes. And next is the module properties. Module properties is 8.2 kg. The length is 0.61 meter and the diameter is 0.16 meter. Okay, next. This is the mechanical drawing of membrane filter. The measurement is obtained from the summary of membrane filter design just now. So the length is 0.6 meters, and then the tube, the diameter of tube is 0.23 meters. Next. Next.
Sorry.
Okay, it's okay.
Approach.
Okay. Okay, next is the cost analysis. So there are two tables. The first table is the cost for ultrafiltration unit. The second table is cost of equipment for UF process. So first table, UF modules has 18 quantities because we have 18 modules, and the unit price is 4,000 with 4,040 ringgit, which total cost is equal to 72,720 ringgit. And then the membrane element is also 18, and the unit price is 2,020 ringgit, and the cost total is 36,360 ringgit. So the total cost only for UF unit is 190,080 ringgit. Okay, and the cost for equipment for UF process, we have 7 centrifugal pump, we have pipes and accessories, which is 20% cost of unit cost for UF unit. Okay, and then we have cleaning material cost. So the total cost is 52,177 ringgit 6 cents. So total of cost for UF unit and cost of equipment for UF process is 161,257 ringgit. And then next is the PNID of membrane filter. So after the liquid went through microfiltration process, it goes to ultrafiltration process. The centrifugal pump is used to move the liquid from microfiltration process to the UF system. And then the diaphragm valve is used to monitor the substance's pressure to ensure that the membrane filter works continuously in an optimal condition, and to ensure that the flow of such series is at optimal operating pressure by controlling the pressure. And then the diaphragm valve is controlled by a pressure controller, and pressure transmitter is used to transfer signal to the pressure controller to control the inlet pressure. After the ultrafiltration process, there is a control valve to control the flow of permeate stream and retentate stream. Flow controller and flow transmitter are installed to ensure that the liquid level is not exceeded the maximum level during the process and discharge of the filtrated syrup after the process. Okay, next. Next is the CIP system. Okay, first UF unit need to be clean. It need to be shut down to clean it. Okay, and then we use softened potable water to wash the UF membranes, and then flush the dislodged white pollens from the device at the usual operating flow for at least 10 minutes, and then get the cleaning solutions back. It is important to prepare the cleaning solution with softened drinking water or alternatively treated water that is free from sparingly soluble salts. And then we warm the cleaning solution to 40 to 50 degrees Celsius because it is much more convenient to clean with warm water than to clean with cold water. And then given the amount of falling that is addressed, chlorine levels should be chosen conservatively. So, and then circulate the cleaning solutions at reasonably high flow rate through the device for 30 to 60 minutes because high flow has a scoring effect, okay, which helps loosen pollens from the membrane surface. And then flush the cleaning solution and rinse the UF membrane with softened potable water until no traces of cleaning solution remain. Okay, next is the HAZOP study for ultrafiltration. This is the assessment for hazard that might happen in the equipment for ultrafiltration system. So there are two parameters, which is pressure and flow. So what happens if there is no pressure in UF system? It may be caused by control valve is not functioning well, so it can delay in the operation. If there is high pressure, it may be because of valve failure, and it can cause explosion or liquid spill. And if there is low pressure, system failure happen and also delay in the operation. Okay, so what can we do is we need to recheck our operating procedure. We need to maintenance regularly, and then we can apply pressure relief valve uh, 4 times. Okay, and then for flow, if there is no flow, it can maybe because of control valve is not functioning well, and it can delay in the operation. If there is high flow, too much material added to the tank, it can cause explosion or liquid spill. If there is low flow, maybe because of membrane falling, and then it's delay in the operation. If reverse flow, pump out of service, failure of water source cause backward flow, and it can cause product offset. So we also need to install alarm, maintain regularly, and recheck our operating procedure. Okay, that's it from me. Thank you.
We'll proceed for the process and mechanical design for GSC adsorption for the decolorization process. And an important step in sugar process where color is removed from the syrup along with other impurities in order to produce as pure and low color crystal as feasible. Color determines the grade of sugar and is the main concern of buyer and consumers. For the process design of this decolorization process, the granular activated carbon in a pack bag is used. The GSC is chosen in the process because it is used in many purification process, including in decolorization for sugar solution. It is also has a high absorption potential for organic compounds such as sugar colorants. Next, this is the summary of the process design based on calculation and assumption. For the pack bag column, granular activated carbon, GSC, and their operating condition. Next, for the mechanical design, the shape used is cylindrical vessel. The height is 15 meter. The diameter is 4 meter. The wall thickness is 12 millimeter, and the head used is hemispherical head. And the nozzle diameter is 0.95 meter, and the lid used is skirt support. Next, next for the cost analysis. Eh, wait. Okay, this is the figure shows the design for the side view and the top view. Okay, next, this for the cost analysis, the major equipment is pressure vessel. The minor equipment are centrifugal pump, control valve, flow controller, and flow transmitter. So the total equipment cost for the discolorization process is 153,599 ringgit and 31 cents. Next, this is the PNID of GSC adsorber. The flow rate of the IMO syrup liquid is control at the inlet stream to ensure that the maximum level of the liquid is not exceeded during the process and that the adsorbed IMO syrup is discharged after the process. In the inlet stream, the flow transmitter will detect the flow rate and send the signal to the flow controller, and the controller will give the signal to the control valve to rise or reduce the flow rate as to regulate required flow rate. This same goes for the water stream. For the backwash flow, the flow will be controlled using flow transmitter, flow controller, and control valve to ensure that its required water will be delivered to the adsorption column system for the backwash process. Next is the CIP for the GSC adsorber. A CIP operation for GSC adsorption is backwash of the activated carbon bed. Periodically activated carbon bed need to be backwashed. To allow backwash in place, a free bird of about 50% should be integrated into vessel design. So the carbon or the adsorbed pollutant are not regenerated by the backwash phase. A safe backwashing control head, a distribution system, and a loaded vessel with carbon are included in the system. Through the controller, the water enters through the loaded vessel top, down through the media, then up through the distribution system, and out to the drainage. A downflow settling or fast rinse is usually followed up with this backwashing cycle. Next, this is the hazard analysis for the GSC adsorption. The parameter used is flow. For the no flow, the causes are the blockage of pipelines and the valve failure. The consequence is no decolorization occur with no feed. For the low flow, the causes are valve partially closed and clogging or falling in pipe. The consequences are longer filling time and interrupt with process scheduling. For the high flow, the causes is broken control valve and the consequences is inefficient decolorization. And the action required um, are maintenance of valve and instrumentation periodically and schedule inspection. That's next. That is for me. I will pass to Hanis.
Okay, thank you, Anis. I will proceed with site layout. So site layout, as sites can be very complex places, requiring the planning and transportation of large amount of materials, as well as high value goods, plants, and people. They are a critical part of building management. So as it can be seen in the site layout, the production zone is placed at the center of the site. This is because it is easy for the loading and unloading products. Um, the administration room and toilet are not directly adjacent to the processing area and separated by a pathway. And personal hygiene facilities such as changing room needs to be adjacent to any production room where operators switch from lower risk to higher risk. It is necessary for the quality control laboratory to be adjacent to the processing space, which needs a quality test to allow sampling. Okay, so next is plan layout. Okay, so this is the plan layout for our factory. Okay, a plan layout is designed to obtain in terms of both quantity and efficiency a physical arrangement of various entities of a facility that most economically meets the required output. So our production zone, as it can be seen, production line is U-shaped layout. Because U-shaped layout has few advantages. First parts input and output are very close together so that handlers can drop off raw materials on the same trip and pick up finished products. And then it can also eliminate the necessary work in process space and make it simpler to supervise and visually monitor operations. Okay. And also it is divided into three risk area, which is low risk area, medium risk area, and high risk area for hygienic zoning program. Okay, next.
Okay, next is waste treatment plan. Okay, for waste treatment plan, the wastewater coming from the process to produce the IMO syrup and also coming from the CIP process. And then okay, the proposed plan for wastewater is firstly the wastewater will be collected into the tank, and then there will be a screening process, and then the grit removal, and then the primary clarifier or sedimentation, and then the aeration. Next one is the secondary clarification. Next is disinfection, and then the effluent discharge. Okay, this one I will explain in detail from the process. Okay, firstly for the wastewater collection. Okay, the wastewater that we produce from the production will be collected and stored in the storage tank, and then it will proceed to the screening equipment to remove any foreign materials such as plastic or debris. And then next one is the grit removal. So this one is there will the equipment will be used to remove any large organic or inorganic substance. And then they will proceed to the primary clarification or sedimentation. And the wastewater will coming to the sedimentation tank or primary clarifier for the initial separation of suspended solid organic matter from the wastewater. And then we proceed to the aeration process, which is at aeration, the air will be pumped to the aeration tank to provide the oxygen for the bacteria to grow and to encourage the breakdown of any organic material that will form the biomass waste. And then the secondary clarification, where the remaining organic sediment will be settled out. And then next is the disinfection. Okay, this infection is to reduce the number of the microorganism in water before it will discharge to the environment. Okay.
This is the economic evaluation. For the total capital cost, there are fixed capital cost and working capital cost. The total capital cost is 18 million 766,517 ringgit. Next. For the total operating cost, there are fixed operating costs and variable operating costs. The total for the total operating cost is 34,672,867 ringgit and 20 cents. Next, this is the summary of economy analysis. The price per unit for our product, there is one box containing 12 bottles. The price is 600 ringgit. The net profit for our process is 17,379,000 ringgit. And for the payback period for our process is 2.37 years. So that's all for our presentation. Thank you.
So any question from the
Any questions, Doctor?
Okay. Can you hear me?
Yes, yes,
Yes.
Yeah. Okay. Kabun here.
yes.
All right. Good to see you guys. Okay. I am a project management team in FNN. So usually when we do this kind of plant design, right? First thing first, we need to know why. So usually we look about the application of this or the potential of this product. I think maybe you guys already presented to your lecturers previously. So maybe you can brief me a little bit on this. Like IMO from rice starch. So maybe you can say like easy to get the rice starch from somewhere and then the IMO to be used in as a what sugar replacer or something. Yeah, Shafiq.
Okay. Okay. This product is basically the IMO. This IMO can be formed with powder or syrup, but we choose syrup because when we have to produce in the powder form, there will be for example like spray drying. So the equipment will be increased. So and then the cost also might be increased. And then for the rice, we use the raw materials. The main raw materials for the this IMO is basically the starch. So we choose rice starch because rice starch is commonly and also rice starch believed to have rice have believe have to have rice to have high content of starch.
Yes, and it is also easy to obtain in Malaysia.
Okay. So sorry, come again. Just now you mentioned the application of this is for what? Powder syrup?
Oh, we choose to produce IMO syrup. We use
Sugar syrup
sugar syrup that we use as a sweetener in baked goods, something like that.
and drinks as sugar substitute.
Okay. Got it. Okay. So Dr. Rabita, Dr. Atika, and Dr. Rosaliza, right?
Yes, Kabun.
Hi.
Hi, how are you?
I'm good. Thanks. So the reason why I asked questions is because I've left this behind very long time ago, I think 9 years. So,
Yeah, Kabun, right? Last time you graduated when I first entered UPM.
oh, I see. Yeah.
Yeah.
back in 2012, 2011.
2012, yeah. Been working for 9 years already, yeah, Kabun?
Yeah. I
Okay,
was,
great.
yeah, for so long already, all the while in project.
In projects, right?
Yeah. So, okay, so the only reference I've been using right now to do the rating is the document that Dr. Nasli sent.
Yeah.
Yeah, so I plan to ask questions based on those PO1 until PO11, is it? PO13.
Okay.
Okay. So I noticed everybody done their own plant, the equipment design, right?
Yes.
So roughly when should I send this rating up to you guys? I mean to Dr. Nasli or Dr. Rabita?
Uh,
Immediately after this or how?
I think that one you have to, can you ask the Nasli back, Kabun? I'm not sure also. And but I don't think it's immediately after this. You have the form, and I
Yes.
think you can take your time. He has to fill in the marks by the end of the semester, so I think it will maybe 2-3 weeks from now still.
Okay. Because I would like to, if you guys okay with that, I would like if you can share this slide with me because I need to. Initially, I was not sure. I thought like everybody design together, but now I notice that you all design individually, right? So I need to look back your design, and then also the final report. So I want to base on those to do the rating.
Okay, no problem.
Sure.
Yes, Mr.
Yeah.
Tan.
Okay.
I will send to you later.
Okay, good. Right. So, is it okay if you can go to the plant layout?
Plan it out.
I think it's slide 62 and 63.
This one?
Yeah, when I glanced through this, actually I don't really understand. Maybe you guys can brief me a bit. Can you look at 62 first? All right. So you see, do you know? Sorry, I cannot say so. I need to understand what is the unloading bay doing and what is the loading bay doing.
Okay, so the loading bay is where the products will be entered the factory, and then the unloading bay is when our finished products go to.
I see. Okay. I only have 9 years of working experience, so I cannot say that you are wrong or you're right, or I'm wrong or I'm right. So
Okay.
I usually people use loading bay as in like goods going into the truck and then going out. But I'm not sure. But from the past 3 factories that I work, loading bay is like the last stop before the goods are going out. Yeah.
Okay.
So maybe the wording here is the other way around. Unloading, we unload the raw mats into the factory and then load the finished goods into the truck and go out of factory. Yeah.
Okay.
So
Okay.
I was confused. Okay.
All right.
All right. Now I
Noted.
understand. Yeah. All right. Good.
Thank you, Mr. Tan.
No problem. Okay. Can you go to slide 63? So, okay, I noticed that some of your equipment, right? They go up to 15 meters, like the evaporators. Correct? So 15 meters is like 7-story, slightly less than 7-story high.
Okay.
So I'm not sure is this following the scale? Because when you design a plant layout, right, you have to factor in your equipment size roughly. Oh, I know this is really but you guys have to look into, like for example, changing room, I think it's too big.
Okay.
So it has to be logical.
Okay.
When you design a plant, it has to be logical. And then you have to cater for future expansion and all those, because when I look at your economic analysis, right, it seems like this is a very lucrative business. Say 100% sold, meaning that whatever you produce, you get to sell. Then I think this is a very good business.
Okay. Thank you, Mr. Tan.
No problem. So what is the risk area that you are mentioning? Low risk, medium risk, high risk?
Oh, for the hygienic zoning, like
I see.
if high risk area means high contamination.
I see. Okay. That's another way of doing it. Yes, you're right over there, but I'm just sharing. Back in Nestle, right, when I was there, they different up the zone by high hygiene, medium hygiene, low hygiene. So it's the other way around.
Oh, okay.
So yours is on the risk. I believe production areas should have high hygiene instead of the administrative office, changing room, or maybe loading bay. Usually loading bay, lorries coming in and out, right? So it should be higher risk
Higher risk. Okay.
or low hygiene, something like that.
Okay.
Oh,
Understand.
okay.
Ah.
I understand.
Okay. Is there any other presentation you'll be carrying out with lecturers, or this is the last one?
This is the last one, I believe.
Yeah, but we have to fix our report
Yes.
before we send to the coordinator.
Okay, I see. All right. But those that I mentioned just now are just for future lah. For example, say you
Okay.
become another project manager in the
Alright.
future, right? Right. All right. Another rating that I notice is for the group rating is the waste treatment and utilization.
Okay.
So from here, when I look at your report, it was stated that the waste is water.
Yes,
Anything else?
water only. But that water contain cook organic materials such as carbohydrate. For example, like starch. There will be the aerated starch in the wastewater, and also there will be fats, protein that coming from that is all the ingredients in the rice starch composition in the rice starch.
Okay. All right. So that's the coagulants and
Population.
coagulants, mainly water coagulants as well as the CIP system lah.
Yes.
Okay. All right. Sorry, I would like to ask a sensitive question.
It's okay.
Sorry, don't mind me. I just want to understand the report. I noticed certain pages are filled with individual's name, although in the rating it is a group rating. So how should I rate this?
Actually, the individual is only the chapter 3 and chapter 4. But there is for PNID and chapter 5 is, if I'm not mistaken. Chapter 5 is there's a requirement for the individual PNID. So the marks given for the PNID is the overall and also the individual. But for waste treatment, the economic
Site layout, plan layout.
is the group.
Overall PNID. Yeah.
Oh, I see. Yeah, I noticed you guys presented BNID and CIP system individually as well, plus the heads up.
Yeah.
Hmm. Okay, no problem. I'll check with Dr. Nasli on this. Because the form I got, BNID, CIP, HAZOP, they are all seems like group. There's only one row.
Oh, okay.
It's not
Understand.
individual. Yeah.
Oh.
So it's like overall. Okay.
Thank you, Mr. Tan.
Thank you, Mr. Tai.
No problem. Welcome. Just a brief one. Wai Xiong, is it?
Yes. Yes, Mr. Tan.
Notice something. Is it that your level sensor 55 ringgit only?
I search on, yeah. But I don't think is, I'm not sure whether the accuracy will be that
Yeah.
that
Okay.
high. Yeah.
All right.
Yeah.
Yeah, I understand because you cannot get quotation from anyone while being in university, right?
Yeah.
Okay, so I think that's quite impossible lah. Even if you go buy from China also, 55 ringgit quite hard to get. So
Okay.
logically, it won't be like that lah.
All right.
So
Then make a change.
it's okay. I'm just sharing my experience. I've been getting quotation, but anyway, every different company, different way of working. So some people will break down every package and buy on their own, tender and buy on their own. Some will get a service provider, someone like JJ Legi, Cronus, someone to build the entire system for them.
Oh, see.
Is it okay? Can I see the economic analysis evaluation?
This one?
Yeah. So what is the ISBL and OSBL?
Okay.
And then the engineering cost? What are all those?
Okay, from what I understand, okay, ISBL is include from the process equipment that we make the new plant. So the based on the calculation, based on the formula from the chemical engineering design. So the ISBL is the formula is the installation factor minus multiply with the equipment cost. And then for the OSBL, I forget. Okay, the OSBL is the cost for cost of addition that must be made to the site infrastructure to adding the new plant. Basically, from the books tell that the OSBL cost is basically the 40% of ISBL cost.
And for the engineering cost is maybe for the business planning, management, for the project management, planning, scheduling, like that.
Okay. So I suppose your ISBL, OSBL covers the building costs, the piping costs, electrical wiring. So all those will come into actually they cost a lot, and then the authority approvals. So it's okay. If one of you guys join plant design or project engineer for clients, then eventually you face all this, and then you have to memorize all this.
Okay.
Okay, all right. So payback time 2.5 years.
Yes.
So why not we run this business? Confident or not?
Confident.
But actually the price for the IMO is quite high, because when I refer to buy Vita Fiber product, that is 400 ml of IMO syrup. This is basically for 50 ringgit, something like that. So the price quite high. So the process also, the cost of the process is also high.
Hi.
All right. Okay. All right. So that's all for my questions.
Okay. Thank you, Mr. Tan.
Okay, I guess it's my turn now. Can you hear me?
Yes,
Doctor.
Okay. Congratulations for reaching this far on your project work. I think this is the final presentation of your IDP. Am I correct?
Yes, doctor.
Thank
Okay.
you, Doctor.
All right. Okay. Most of the question has been put forward by Mr. Tan. So I guess I'm just interested to know a little bit on the design of your equipments. Let me start by Wai Seong. Can I know, when you design your agitator unit, I see here that you use anchor agitator. Can I know, in terms of the arrangement of this anchor agitator from the bottom of your vessel, can you let me know what is the distance of your agitator against the vessel bottom?
So the agitator that have been designed, assume that the anchor length, I did not specify the actual height of the agitator, but yeah.
So do you reckon that your fluid height will be occupying how many % of your vessel?
It will be occupying around 70%.
So in terms of height, what kind of height would that be in your design vessel?
Hello, sorry, doctor, can you repeat? Just now my laptop hanged.
In terms of fluid height in the
Yeah.
vessel, yeah, can you just just quickly give me the measurement?
The measurement, I didn't calculate it.
So 70%, it's in terms of volume, isn't it?
Yes.
Okay. Now my question is, do you think your impeller has to be further than your liquid level in the agitator, in the
Further
vessel,
than liquid.
in the vessel?
I think the liquid level, the agitator impeller may not really need to be higher than the liquid level.
Okay, right. So in this case, your anchor diameter is 0.8 meter. Do you know what is the best position of this impeller against the bottom of your vessel?
Best position. I believe it is because there is no actual design that I really found through the internet on the Anchor design. So I may assume on 10% or 20% from the bottom of the tank.
So do you refer to any standard when you design your agitating unit?
I did not refer
You don't refer. I think
because really can't search any related. Yeah.
I would suggest you to go and find information on designing an agitation unit vessel. I'm sure you can find a common or a generic ratios. Yeah, they would have ratios in terms of the diameter of the impeller, the diameter of tank, in fact, the height of the liquid. So that would be a good reference if you were to design an agitation vessel. So I would recommend you to go and have a look at that.
All right. So that refer to any types of agitator.
Yeah, it is. There is a standard, or there is a generic or typical design for an agitator vessel, where they give you the ratio of the dimension of important dimensions in in agitated vessel.
All right. All right,
Okay.
doctor. Okay.
All right. Next, I'd like to move to Shafika. You are also designing a bioreactor with an impeller, correct?
Yes, doctor.
Okay. Now, I would like to know what kind of viscosity of fluid that you have in the reactor.
Viscosity.
Yes.
Okay. Based on I use the assumption and 1300 CP.
1300, 1300 CP.
Ah.
As compared to the fluid that Ysong is working with, which one do you think it's more viscous? Your liquid or Ysong's?
I think the product from my reaction, where there's a lot of sugars, oligosaccharide.
Mm-hmm.
So the liquid is more viscous.
Okay, right. Can I know what kind of impeller that you are using in your reactor?
Rushton disc impeller. Rushton disc impeller.
Ruston disc impeller.
Ah.
Okay, can you tell me what is so special about this impeller?
This impeller is the flow, the radial that will the flow is radial
Mm-hmm.
that will move the fluid sideways during the rotation. So the mixing process is more convenient.